Hi guys, this is geometry. Let's look at topic 7. Topic 7 is about similarity, and topic essential question is how are properties of similar figures used to solve problems? We have 5 lessons in this topic, and we're gonna explore similarities in triangles overall. So the important vocabularies for this topic: the center of dilation, geometric mean, similarity transformation. Okay, let's look at our first lesson. Lesson 1, dilations. We'll start with dilations. In this lesson, we'll be able to figure out how to dilate figures and identify characteristics of dilations. And the important vocabulary here is the center of dilation. Let's look at explore and reason. Roosevelt High School sells a sticker and a larger car decal with the school logo. As you can see, we have the logo shown here. So part A, look for relationships. How are the sticker and the car decal alike? How are they different? Okay. So stickers are the smaller ones and a larger car decal is the bigger one. How are they similar? How are they alike? And how are they different? What do you notice? They look the same, but their sizes are different, obviously. But how could you describe using shapes and angles? Okay. So for example, if your friend has the sticker but has not seen the car decal, so your friend only knows the sticker, how would you describe the car decal? You can say that the shapes and colors are the same as the sticker, but the decal is larger, right? And what happens when you zoom in on a computer screen, for example? So part B, or let's go ahead and write part A down. I'm gonna write part A over here. Okay, you can say they have the same shape and the same angle measures. What's different? They are different because the side lengths and height of the R in the decal are twice that of the sticker if you measure them. We're going to say about twice. Okay, that's part A. And so part B, suppose the sticker and decal are shown next to each other on a computer screen. If you zoom in to 125, so if this is 100, you zoom in 125, what would you say? What would stay the same on the figures? What would be different? So what happens is you zoom in on a computer screen. So if this is the original one, you zoom into the computer screen, what happens? The images and the font sizes get larger. If you zoom in, you can see less of the image. So like 7.1 here is cut out, right? When you zoom out, you can see 7.1. When you zoom in, when you zoom in like that, you can't, right? The fonts get bigger, the shapes get bigger, but your computer screen size stays the same, right? The size of your screen stays the same. So but the shapes and angle measures would stay the same. Like, it's not like the shapes are going to be different. It's still the same thing, right? But the sizes would increase by 25%, right? So you can say that the shape and angle measures would stay the same, but the size would increase by 25% because images, font sizes get larger let's say when you zoom in, images and font sizes get larger. But you see less because the size of the screen stays the same. There, I think that's accurate enough. So in this lesson, we'll continue to think about how does a dilation affect the side lengths and angle measures of a figure. Let's look at example 1. Dilate a figure. How can you draw a dilated image? Do you remember what dilation is in transformation? Yeah, it's when you stretch or compress your shapes. So you're going to have a factor to multiply or divide by when you're using dilation. Okay, so dilation produces an image that's different size than the pre-image. So method 1, we're going to talk about the ratio method. There's a vocabulary here. When you dilate triangle ABC, the bigger one, by a factor of 1/2, so A prime, B prime, C prime is 1/2 the size of the original triangle ABC. And you have a fixed center P that helps the dilation. This fixed center here is called the center of dilation. And what does it have to do with this dilation? So when you have the center P, that's how you can draw a dilated image with your own hands. So step 1, you're from point P, you're going to draw rays from P through each vertex of A, B, and C. Okay, that's your first step. And then you're going to mark point A, where it's half the distance from P to A, because we're dilating the figure by 1/2. So if we pick any point P and then draw a ray through point A, that distance needs to be cut in half. And then that's where your A prime could be. But your point doesn't move for other points so that your triangle stays the same shape. Okay, and then you connect the dots. That's your new dilated figure. The triangle A prime, B prime, C prime is a copy of triangle ABC with side lengths that are half the lengths of the corresponding sides of ABC. All right, this is another method, the parallel method. So for this one, we're gonna dilate the figure by multiplying 2. So we want to dilate WXYZ by 2. That means it's getting bigger with center of dilation Q. So you want to draw a bigger shape. It also works for smaller shapes too. Like the parallel method is not only for dilation to get bigger. It works both ways. It's just a different method, okay? So step 1, you have a center of dilation Q in the figure, and then you're going to draw rays from Q passing through the point, the vertices, and then you want to increase the distance by 2. Okay, so then that's your new point. And then from Q to X, you draw another Q to X. the distance from Q to X to the same extended line. Then you're gonna mark the point X prime. Same for Y prime, Z prime, and then you're gonna connect the primes, and then that's your new figure. That's twice as big as your original figure. Okay, so first method, point center of dilation outside the figure, and then measuring your distances outside a figure. And the second method, it's the parallel method where you have the center of dilation inside your figure. Okay, let's look at try number 1A and B. Trace JKL and point R. Your center of dilation is inside this triangle. You're gonna use method 1. Okay, even though it's inside your triangle, you're still gonna use method 1 to dilate JKL. So even if it's inside, you're going to put rays for all the vertices, and then no, I think that's method 2. That's supposed to be method 2. It's a typo. Method 2, and that's method 1. Okay. To dilate by a scale factor of 3 with a center of dilation R. Okay, so then you draw straight lines here and then measure the distance here. That should be the same as the distance over here. That's going to be K prime. And I know it's hard to use my ruler when I can't really see it physically on the screen, but right here. So you're gonna draw a line, a ray through point L, and then put L prime around here, and then you're gonna draw a ray through R to J, and that also needs to be the same distance. Okay, J prime. And then, so you need to measure the lengths as you go, right? Because you want the lengths to be equal. There. And then you connect all the dots. And that's where you can see the dilated figure. There. So that's our triangle J prime, K prime, L prime, where we dilated JKL by a factor of 3. Oh, it's by a factor of 3. I'm so sorry. This is by a factor of 2. So you need to multiply by 3. So then you have to do another length over here, another length over here, another length way down there. So it's gonna go across, like out our paper. So if you have a separate piece of paper, you can trace it and draw it. Okay, part B. Trace PQR and point M, and then you're gonna use method 1 to dilate triangle PQR by a scale factor of 1/3. So then, you're gonna measure the distance from M to P and then divide it by 3. And now that's your new P prime. And then M to Q. Okay, this is method 1. Divided by 3, and that's Q prime. And then M to R divided by 3. That's R prime. And that's gonna be your new triangle. That's 1/3 the original triangle PQR. Okay, so use the appropriate methods when you can. So the concept of dilation, a dilation D, it's notated capital D. Capital D sub N comma C is a transformation that has center of dilation C and scale factor N, where n is greater than 0 with the following properties. Okay, that n comma c is where you have the scale factor n, and then c is the center of dilation. So it's a name. So over here, okay? So these are some properties we have. Point R maps to R prime in such a way that R prime is on CR, ray CR, and CR prime is equal to n times CR. Okay, this is the first one. Each length in the image is n times the corresponding length in the pre-image. Okay, and the image of the center of dilation is the center itself. And if n is greater than 1, the dilation is enlargement, because you multiply, if you multiply by a number greater than 1, then it gets bigger, right? If n is between 0 and 1, the dilation is a reduction, okay? It gets smaller. What if it's a negative number? Then it's not a dilation anymore. Negatives are for, we learned this in Algebra 1, but if you have a negative factor in transformation, that means a reflection. It's a totally different transformation, okay? So dilations only deal with the positive numbers, positive factors, okay? Every angle is congruent to its image under the dilation. On a coordinate plane, the notation D sub n describes the dilation with the origin as a center of dilation, okay? So origin, you don't need a P. So on the coordinate plane, your center of dilation is always going to be the origin 0, 0. Okay. All right, let's look at the next example. Example 2, analyze dilations. Rectangle A prime, B prime, C prime, D prime is a dilation with a center P of ABCD. How are the side lengths and angle measures of ABCD related to those of A prime, B prime, C prime, D prime? So first you can compare the angles. They all have right angles, so they're both rectangles. You can compare the side lengths. AB is proportional to A prime, B prime, and all the side lengths are proportional. So they have the same ratios of 3, right? So from the smaller rectangle to the bigger one, you have a factor of 3. That is your factor of dilation. The ratios are equal, so the lengths of corresponding sides of the two figures are proportional. That's the important thing for example 2. So let's see if you can do try by yourself. Come back when you're ready for answers. Okay, so rectangle W prime, X prime, Y prime, Z prime is a dilation with center P of W, X, Y, Z. How are the side lengths and angle measures of the two figures related is the question. So from here to here, you should always remember that the primes are for after the transformation. So X, Y, W, Z is your original figure. X prime, Y prime, W prime, Z prime is your image. So pre-image and the image, okay? Before and after. So how are they related? Are they exactly the same? The angles are the same, they're rectangular, right? They're perpendicular. And X, Y is 1, 2, 3, 4, 5, 6, right? X prime, Y prime is 1, 2. Are they proportional? Well, let's see the other sides. XW is 3 in length. X prime, W prime is 1. So 3 to 1, is it the same as 6 to 2? Yeah, 3 to 1 is the same as the equivalent ratio to 6 to 2. So from 6 to 2 and 3 to 1, what happened? What is your scale factor? Are you multiplying by 3 or are you dividing it by 3? You're dividing it by 3. So what can you say? How are they related? The corresponding side lengths have a ratio of 1/3. Okay. And the corresponding angles are congruent. Okay. There. Okay, example 3. Find the scale factor, just like that, right? Quadrilateral J prime, K prime, L prime, M prime is a dilation of J, K, L, M. What is the scale factor? So starting from the black figure, we're gonna dilate to the red figure. So we know it's visually getting bigger. So you know it's gonna be greater than 1. Okay, but how do you know? Well, you compare the lengths, 12 to 18. So how do you get the factor that multiplies to 12 to get 18? So in other words, you're going to multiply 12 times x to get 18. In order to get x, what do? 18 divided by 12. So 18 divided by 12 is 3/2. That is our scale factor. Okay, scale factor. That is the important vocabulary here. Scale factor is a ratio of side lengths in the image to coordinate corresponding side lengths in the pre-image. Let's look at try number 3. Consider the dilation shown. So dilation and enlargement or a reduction. Where are we starting from? What is our image? What is the scale factor? Okay, so look at the triangles A, B, C, and A prime, B prime, C prime. As I mentioned before, A, B, and C is gonna be the before. A prime, B prime, C prime is the after, okay? From here to here. So is it an enlargement or a reduction? Did the triangle get bigger or smaller? Got smaller, right? So it's a reduction. Okay, what is the scale factor? We need to figure it out. So you can count 1, 2, 3, 4. 4, 2, 2. And 2, 2, 1. So what is the scale factor? 2 to be divided into 1. You need to divide by 2. 4 divided by 2 is 2. So your scale factor is multiplying it by 1/2. That is 1/2. Okay, so always consider what your numbers are becoming. So 4 to 2, it's a reduction. So you're multiplying a scale factor that's less than 1, greater than 0. Okay. Let's look at example 4 in the next page. Dilating a figure with center at the origin. What are the vertices of dilation sub 3? Triangle ABC. So for the coordinate, what does this mean? Dilation sub 3. The notation dilation sub 3, D sub 3, triangle ABC means you're dilating triangle ABC, and it's for the coordinates, it's always going to be centered at the origin. So whenever you don't see a point of dilation, that is when you have the center at the origin. Okay, with a scale factor of 3. So that is your scale factor. Okay, so from the origin, that is your point of origin. You're gonna dilate this to the scale factor of 3. So you can count the slope. You go up 2 over 1 here, behind 1 over here. So you do the same thing, up 2, behind 1, up 2, behind 1. So that is your straight line, right? And your scale factor is 3. That's why we do 1, 2 more times, right? So that you have 3 equal lengths of the same line. So that is your final point for B prime. Okay, same thing for A. You can count the slope. Down 1 over 2, down 1 over 2, down 1 over 2. So that is our straight line. And we have 3 equal side lengths. That is your endpoint for A prime. Same for C, 1, 2, 3. You just go 1, 2, 3, and another 1, 2, 3. That's C prime. And then you connect the dots. Sorry, it's not straight. And that's going to be your dilation of triangle ABC by the scale factor of 3, center at the origin. There you go. Okay. So you can count the slopes, or using the points, you can simply multiply 3, the scale factor of 3 to both vertices, x comma y. Okay, so 3 times 2, 3 times -1. 3 times -1, 3 times 2, 3 times 3, 3 times 0. Okay, that's going to be your vertices algebraically. So let's look at triangle number 4. You're going to use this triangle PQR. What are the vertices of the dilation scale of the scale factor of 1/4, center at the origin of this triangle? And how are the distance to the origin from each image point related to the distance to the origin from each corresponding pre-image point? Okay, so think about this and see if you can solve it by yourself. Come back when you're ready for answers. Okay, so first step, you're gonna label the vertices. So P is going to be 8, 4. Q is 12, -4. And R is -4, 0. 2, apply the scale factor. So I'm going to use a different color. So if you use the scale factor of 1/4, you're going to multiply 1/4 into both x and y. So 8 divided by 4 is 2. 4 divided by 4 is 1. Okay? So that's P prime. And then Q prime multiplied by 1/4. So 12 divided by 4 is 3. -4 divided by 4 is -1. That is Q prime. R prime. So multiplied by 1/4. -4 divided by 4 is -1. 0 divided by -4. 0 divided by 4 is 0. That is your R prime. So the vertices you have is P prime is 2, 1. Q prime is 3, -1. And R prime is -1, 0. You can graph them, although they don't ask you to graph them, to check if your answer is reasonable. That is P prime, Q prime, and -1, 0 is right here, R prime. There. Does it look like it's similar? Yeah. So how are the distance to the origin from each image point related to distance to the origin from each corresponding pre-image point? How are they related? You have the scale factor. So can you describe using the scale factor? Each image point is 1/4 as far from the origin as the corresponding pre-image point. Okay, just like I graphed it earlier over here, right? You're gonna look at the distances. Okay, so you can also count your distance and according to the origin. So from the origin to this distance, the image point R prime is going to be 1/4 the distance of the original R, okay, from the origin. All right. I think this is the last example. Let's look at example 5, dilating a figure with center not at the origin. So what if they specify a center and it's not at the origin? What are the vertices of dilation of the scale factor 1/2 around the center of dilation R QRST. So you're going to dilate this in the center of the point R. Okay, then you're gonna shrink the distances from that point R. So that means your point R stays the same, but your S is gonna go closer. T is gonna go closer. Q is gonna go closer, right? Because 1, 2, 3, 4, 5, 6. That is 6 distances away from R, right? But S needs to go half the distance. So 1, 2, 3. Now that is where S prime is. Same for T. So you can use the coordinate points to divide all the coordinate points by 1/2 if you are solving this algebraically. So visually, you're dividing the distance in half from R, but visually, how do you know how to divide? Because if it's not origin, you can't just divide all the numbers by 2, right? So look at this chart. Pre-image point is labeled here. They're labeled here. And then change, you need to find the change from R, point R, so that you know the distance. Now half the change from point R is your calculation. And then you add it to the R so that that's how much distance you're away from R. And then that's how you get the image point. Does that make sense? So R is -2, 7, and then S is 4, 7, and the change from this point is horizontally the change is 6 apart, but then vertically you don't change. So horizontally, you can just calculate the distance that needs to be half, which is 3. And then you're going to add it to this point. And vertically, it still doesn't change. Okay, so that's why you add 3 here, but add 0 here. Okay, but if you have a change both horizontally and vertically, just like point T, 4, -1, your change from -2 to 4 is 6. Your change from 7 to -1 is -8, right? So then you're going to divide that by 2, and then that's going to be 3, +3 and -4. So you add +3 on -2, and then you have 1. 1, 7 minus 4 is going to be 3. So right here, 1, 3 is your new T prime. And same for Q. Okay, and then that is your half rectangle after dilation. There you go. Okay, when your center is different, then it gets a little bit more complicated. You can't just divide all the coordinate points in half or multiply by your scale factor. You need to find the change horizontally and vertically, both horizontally and vertically, and then use the scale factor to multiply that change, not the vertices, okay? And then you're going to apply that to your point of dilation. Okay, let's see if you can try number 5 by yourself. Come back when you're ready for answers. All right, so the center of dilation, you can't just say point A. Okay, obviously from ABC, you're going to enlarge your triangle to ABC prime, right? And your point of dilation seems to be A because A doesn't move. And B's distance, C's distance move further away from A. Okay, that's the center of dilation. But what is your coordinate point of A? A is -2, -1, okay? Please specify your coordinate points. What is the scale factor? How do you know? How do you know? Well, you can compare the coordinate points from -2, -1. How did C change and how did B change, right? C from 2, 3 became 4, 5. So from 2 to 4 and 3 to 5, what happened? 2 to 4 and 3 to 5. What happened? Okay, but we're not comparing the coordinates. We're gonna look at the distances. Okay, the changes from -2 to 2 is 4. Okay, change from for the x. So let's do horizontal change. Horizontally, change is 4, and vertically, change is -1, 2, 3 is 4 again. But then the change from point A to C prime now is -2 to 4. So this changed horizontally to 6. And this -1 to 5 is also 6. So now we have the same ratio, 4 to 6. What happened, right? In order to get the scale factor, you divide 6 by 4, the greater one by the smaller one because it's an enlargement. And then you get 3 over 2. That is your scale factor, 3 over 2. In order to check your answer, you can check point B as well. Point B is -3, 1. B prime is it looks like -3.5, 2. So the distance from A to B was horizontally, let's see, 2. Wait, horizontally is 1. And then vertically, -1 to 1 is 2. Okay, and then you multiply scale factor, 3 over 2. So the distance horizontally is going to become 3 over 2. And then 2 becomes 3. And so you add them to the point, -2 plus 1.5 is it's a negative change. So you got to add -3.5, -1.5. So that's -3.5. Then from -1, you add 3 to get 2, and that is your B prime. Okay, checking your answers. Your scale factor works. All right, so that's how you can find your center of dilation and the scale factor in coordinate plane. Oh, we have another example. I'm sure this is the last one since it's an application problem. Solve population density problems. County planners are considering dividing Mott County into 4 equally sized administrative zones. Each zone is a dilation of the county as a whole with scale factor of 2. So each zone is a dilation of the whole thing by a scale factor of 2. Basically, you dilate by half, shrink it by half, and that gives you 4 equal parts from the whole. Okay, what would be the population of each zone if it has the same population density of the county as a whole? What is a population density? Population density is a measure of the number of people in region divided by the total area. Okay, so the whole population is 388,643. Okay, so we're not just getting how many population is for each area. Population density is a measure of a number of people. So you first find the number of people per area, and then you divide by the actual area. Okay, so the question is not just how many people are living in each area. Population density is a different problem, okay? So first, you want to find the area of the whole thing. So area of Mall County is going to be 39 times 48, and that's 1,872. If you divide that by 4, you get an area for 1, right? One zone. But for the whole thing, you divide the population 388,643 by the area 1,872 to get the population density of the whole thing. Okay, it's 207.6 per square miles. So if the population density is the same, you're going to find the area of one of the administrative zones. You can divide the area. You can divide the dimensions by 2 and then multiply them to get the area, or you can divide the area by 4 because it's gonna equally divide into 4 equal parts. And you get 468. So this area, this is the whole, and then this is the area of one zone, okay? And then your population density stays the same. So using that, population density is the population divided by area. So you want to find the population for one zone. And that's 97,156.8. Okay. And that's actually accurate. How do you check? Because if you divide the whole population, 388,643 by 4, you get 97,160.75. So it's actually, you're actually saying, oh, if the population density is equal for all the zones and it stays the same, then you can basically divide the population by 4 and say, oh, all the populations live in the zone equally. But using the population density, this is how you can prove the population density stays the same and the population, how to get population. All right, try number 6. Suppose the population of zone 1 is 102, 981. What's the population density of zone 1? What's the population density? You divide population by area. So divide this by area, 102, 981. Wait, I'm not going to write my work here. Let's do here. 102, 981. Is the population. Your area of one zone is this divided by 4, right? So that's 468. So this divided by 468 is your population density. That's square mile dimensions, and that's one population person. Okay, and so that's gonna be about okay, let me use a calculator. 102,981 divided by 468 is 220. 220, about 220 per square mile. Okay. And if the dimensions Okay, and what's the population density of zones 2, 3, and 4 taken as a whole? It should be the same thing, right? They're the same. Okay. You might have a different example 6 for your textbook. Okay. You might, if you have a similar textbook, like a different version of this textbook, you might have a blueprint example, and that's actually a better example of the scale factor. Okay. Okay, let's summarize our lesson. So basically, today, what did we learn? We learned about dilations. A dilation is a transformation that maps point X to point X primes such that X prime lies on the vertex CX, and you can say if you multiply the scale factor from the original distance, you'll get the distance of CX prime. Okay, dilations preserve angle measures. Your angles stay the same. All right, that was lesson 7-1, dilations. If you have any more questions, please feel free to ask Ms. King in class. Otherwise, I'll see you in the next video. We'll talk about similarity in our next lesson.